Good morning, respected teachers and my dear friends. So this is Chavan Shinde from Shri Shivaji Science College, Amravati, BSc third year. So today, what I'm going to do is a simple experiment actually. It's a frequency response of a common emitter amplifier. So basically, I'm going to define in this what is an amplifier, what are the frequency responses, and what is actually a transistor doing over in this circuit. So let me move on to a circuit diagram first. As you can see on the screen, this is the circuit diagram. Now over here, let me talk about a bit of these components in the circuit diagram. There are not much components in the circuit diagram. Few of the components are resistors, capacitors, and a resistor and a voltage source. Thing I want to emphasize here is these three capacitors. These are the capacitors which actually circuit. Why we actually here I'm going to discuss why in this circuit. So first of all, discussing the circuit diagram about this C capacitor. C capacitor is nothing but a emitter. This is connected to a emitter terminal. The PN junction. This is the NPN transistor. PN transistor, and this is the collector terminal, and this is common. This is the emitter capacitor. So why it is here? First question: why it is here? We know that the resistance is here. We have used the capacitor in order to bypass resistance. Now, why we need to bypass the resistance? At low frequencies, when we are going to study the frequency response of this circuit, at the low going to happen is this that at low frequencies the resistor is going to work in a good manner. But as we move towards the high frequencies, the resistance is trying is the resistance shows some distortion. As you can see, the resistance what resistance tries is at the higher frequency, it tries to shift this Q point you see on the screen from active region to towards the saturated region, because of which the circuit doesn't work properly. That's why in at the higher frequency to we need to bypass it. So using here a capacitor only. Why can't we just use a simple resistance? The reason behind using a capacitor here is that we know RC circuit. In RC circuit, we know the fact that at high the capacity reactance is very low. At higher proportional relation. That's why at higher frequencies, what happens? The resistance of this circuit is low and resistance of this circuit is high. That's why current takes the that is of the low circuit. That's why it moves through a capacitor. That's why we use a capacitor. We bypass this resistor with a capacitor, and it's quite necessary further also. So let me come to here coupling capacitors. These two capacitors, which are just sides of the transistor. These are, as the name suggests, these are the coupling capacitors. Capacitors are used in order to couple the circuit with the transistor circuit, and this CC2 capacitor is used to couple the resistor circuit with the output circuit or the load circuit. Okay, because I don't because it is not so that it is only used in order to couple the capacity. It is only used to couple the circuit, because in that case we could have also used a resistance, or we could have also used a simple wire. But it is also acting as a filter over here. The thing that tells us about that it is acting as a filter, we have AC source over here, but because of though it is a AC source, there are certain distortions of the DC current. In order to block this DC current, which might prove as a distortions into our output, we need a capacitor over. As we know from the basic electromagnetic theory that capacitor only works on the AC current and simply Maxwell's relation. That's why as the capacitor only works on the AC current, we can fit over as a filter to block the DC circuit. That's what its main job is, to block the DC current and to only to flow. Now coming to the forwards, it is also in order to couple this voltage circuit to this voltage biasing, and transistor NPN transistor, and this capacitor is used in order to couple the transistor and output circuit. Now just coming to the slides forward, as I mentioned about the CE capacitor, it is used in order to maintain the operating point or the quiescent point in the active region. Moving forward, that is the bypass capacitors. Why we use the bypass capacitors? Okay, now the coupling capacitor or the blocking capacitors. As this is suggesting, an amplifier amplifies the given signal. In order to be noiseless signal, it is necessary to block the DC, that is direct current should not overload. So we use the blocking capacitors. Now let's move to the most important point of this experiment, that is the frequency response. Okay, let me show you the graph first. So this is the frequency response. Now what you can see from the frequency response is that this is the low frequency domain and this is the high frequency domain, the mid frequency domain. In the low frequency domain, we can find that the voltage gain or the current gain is low. And even at the high frequency domain, the voltage and the current gain is low. Now, what factors are effective? What factors are proving vital in order to do so? So, first factor is that in the in low frequency domain, we know that at the low frequency the capacity reactance is very low, is very high actually. At the low frequency the capacity reactance is very high. That's why the if I move to the circuit diagram, so capacity reactance of this C7 capacitor is high. That's why the less current is moving through the base. That's less is moving, so that's why we are getting less current on the output circuit, and that's why the less. While in the higher region or high frequency, can see that there is also a low decrease in the gain. The reason behind it is the this capacitor. Okay, let me actually I have mentioned the reason, but we do discuss forward. Voltage decrease at the low frequencies. Okay, what happens at the high frequencies? Okay, again, so considering the same point, we know that the capacity at the high frequencies is very low, because of which a high current can flow through the CC1 capacitor, that is coupling capacitor 1, that is connected to the base. So the capacitor behaves as a short circuit as a result. The loading effect. Now what actually is the loading effect over here? Loading effect, in order to talk about the loading effect, I want to talk something about this load. That means load means the output circuit. The output at higher voltage, actually the voltage drop across the output circuit is very high at the higher frequency. That's why the ratio of the output voltage to the input voltage becomes low, and output voltage is to the input voltage is simply called as the gain or output current, or input current. That's why at higher frequencies the gain is very low. Now the important thing to discuss over here is what happens at the mid range, so that we see what happens at the mid range, so that the here voltage gain and the current gain, that means both the gains are constant. Now this capacitor can be also called as the RC coupling capacitor, as the name suggests. R and C, only R and C components are used. At the same time, this can also be used as a filter in order to filter low frequency signals and the high frequency signals because of this region. So this region is very important region, and talk about this region a bit. Now the mid frequencies. Now as we know that at higher frequencies the capacitive reactance is very low. That's why the voltage gain and the current gain is gonna increase. But it's constant over there. That's why there must be certain factor that is also reducing the voltage gain and the current gain. So what's that factor? Is the loading effect. Loading effect is simply the output circuit. We have output circuit, and at the higher frequencies, what we have at higher frequencies, what happens is that at higher frequencies the voltage drop across this output circuit. Okay, the voltage of this output circuit is very high. Because of the voltage drop is very high across this output circuit, the gain is very low. That is the ratio of in output voltage to input voltage. Therefore these two factors, that is the impedance, that is the reactance of the capacitor at the high frequencies, and the other factor, that is the loading effect, simply cancels each other, and which maintains the constant voltage in this region, which is known as bandwidth region. Bandwidth region actually simply I can define as the region in which the 70% of the maximum value, actually we plot which frequency, that is 70 which gives us the 70% of the output voltage or output current. Moving the experiment, how to actually perform the experiment. So this is the experiment. Actually there's nothing much in the experiment performing, because we have to set just these values, keeping we have to set the source voltage at 50 source voltage at sorry 50 millivolts, then source resistance at 100 ohm, source set collector resistance at 4000 ohm, and so on. That's not that important, but let's move on to this experiment that I have performed actually previously, and this is the experimental response that I got. Now, so let us just move on to the experiment here. So this is the experiment that we can see on the virtual lab. So these are the various, this is the resistance, this is the resistance capacitor. Okay, so now here is the panel. Now in the control panel, what we can do, we can by moving, we can set the various values of the capacitor and the resistances. I have just to set the value. So load resistance at 4.2 ohm, base resistance at 10,000 ohm, So this is the capacitors, 10 microfarad capacitors or capacitor. What we are gonna do over here is that we are gonna vary the frequency. Okay, we are gonna vary the frequency over. Let me just vary the frequency in regular intervals. This is for 50 hertz. Okay, sorry. Then if I move it slightly forward, okay, the base resistance. Maybe 10,000. Just a minute, 10,000. 10,000. The peak at 47,000, 410 microfarad. This one is also 10 microfarad. 10 microfarad. Now we can plot diagram. We simply plot the graph. Okay, at 12. Then again going for. So just simply increasing the regular interval or regular interval work. So I'm just showing here the diagram. So if you click on the plot, the graph will be like sort like this. Okay, means this is constant region, but let me move on to the other slide. Okay, so this is the graph frequency response that I have. So this frequency response, as you see, these are low frequency domain, the high frequency domain, and this is mid frequency domain. Mid frequency domain, you can as clearly see from here that the voltage gain and the current gain, or simply calling the gain, is near over this region. So this is what we have to do actually to realize in the experiment. This, as you can see from the screen, so if we change voltage, even we change the frequency, this is the voltage, the gain is constant for most of the frequencies. It starts decreasing for frequency of nearly 0.144 into 5 into 10 to the power 10 hertz. So moving on. Okay. So this was the frequency response actually. This was this kind of frequency response we are gonna get from the common emitter circuit. Common emitter circuit, and it can be in the next the so here is that why can't we use a common base circuit or a common collector circuit as an amplifier here? The reason is the main application or the main on which the amplifier works is the output current mere function of an input current. As in the common base and the common collector circuit, output current is not. That's why we cannot use it as a amplifier. So there are the rings that I have plotted. Okay, yes, sir.
Sir?
Yes.
Okay, sir. Good afternoon, everyone. My name is Deepika Sharma. I am in BSc final year at MSP Art Science and KPT Commerce College, Manora. My topic name is BJT Common Emitter Characteristics. Contents are: firstly, aim of the experiment. Then we will discuss about apparatus, theory of the experiment. Then what is BJT? Then characteristics of BJT, precautions and references. Aim of the experiment is to study input and output characteristics of NPN bipolar junction transistor in common emitter configuration. Apparatus required for these experiments are BJT, breadboard, resistor, connecting wires, ammeter, DC power supply, and multimeter. Theory. First of all, we will see history of transistor. In 1904, first vacuum tube is invented by John Fleming, and vacuum tubes were only technology available at that time to amplify electrical signals or serve as switching devices in electronics. But the problem was they were expensive, consume a lot of power, and gave off too much heat. So after that, in 1947, John Barden, Walter Brattain, and William Shockley discovered the first transistor, which is called as point contact transistor. And this transistors is small and uses much less power than vacuum tube and more elegant solution to the needs of electronics. Then after that, in 1948, William Shockley introduced the improved bipolar junction transistor. So this is the history of transistor. Then what is transistor? The word transistor is a combination of transfer and resistor. It transfers the resistance from one end of the device to another end. A transistor is a three-terminal electronic device made up of semiconductor material. In this, we can see this is the transistor, this is emitter, this is base, and third is collector. There are three terminals of the transistor. Emitter, this is a heavily doped region and its main function is to supply majority charge carriers to the base, either they are electrons or holes. Then second is a base. This is lightly doped region and it is central region of the transistor and it is very thin as compared to the emitter or collector. Then third is a collector region. This region is slightly greater than the area of emitter region and it collects the majority charge carriers from the base. So this is all about the transistor. Then types of transistors. Transistors are mainly of two types. Firstly, BJT and second is FET. BJT is a bipolar junction transistor, which is also again divided into two types. First is PNP transistor and second is NPN transistor. Then FET, which is a field effect transistor, it is again divided into two types. JFET, junction field effect transistor, and MOSFET is a metal oxide semiconductor field effect transistor. So these are the two types of transistors. Here we can see this is the BJT NPN transistor and this is the MOSFET canal N transistor. So these are the types of transistors. Then what is BJT? Means bipolar junction transistor. It is a device which amplify input signal, is called as a bipolar junction transistor. It is operated on the flow of both the charge carriers, which are electrons and holes. So it is called as bipolar. There are mainly two types of bipolar junction transistor. First is PNP transistor and second is NPN transistor. Here we can see this is the PNP transistor, in which N type of semiconductor is sandwiched between the P type of semiconductor. And this is the symbol of PNP transistor. Here we can see the arrow head is towards the base. This arrow is indicating the flow of conventional current. So it means that the current is flows from emitter to base. So this is called as the PNP transistor. Then second is NPN transistor. In this NPN transistor, N is emitter, P is base, and N is collector. P type of semiconductor is sandwiched between the N type of semiconductor. Here is the symbol of NPN transistor. Here we can see the arrow head is towards the emitter. So the current is flows from base to emitter. So this is BJT and its types. Then this is the circuit diagram of common emitter. In this, this is the NPN type of transistor. Here we can see the arrow is towards the emitter. So the current is flowing from base to emitter. This IB is a input current and VB is the input voltage. IC is the output current and VC is the output voltage. Here we can see this base emitter region is a forward bias and collector emitter region is a reverse bias. And in this, the emitter terminal is common between the input and output. So the emitter terminal is connected to the ground. Then input characteristics. In this, the curve between input current IB and input voltage VB constant at collector emitter voltage VCE. The input characteristic resembles forward bias diode curve. IB is input current, VB is input voltage, and VC is the output voltage, which is kept constant. If we observe the input side of the common emitter configuration, N side is connected to negative and P side is connected to positive. So this is similar to forward bias. So in input characteristics, we will get a graph which is similar to forward characteristics of diode. So current increases linearly. At constant VC is equal to 0 volt. As we increases the at VC is equal to 5 volt constant, the graph will start shifting in the right side. So this is all about the input characteristics. Then output characteristic. This characteristic shows the relation between collector current IC and collector emitter voltage for various values of base current. In this, the characteristics, the change in collector emitter voltage causes small change in current for the constant base current, which denote the dynamic resistance, and the ratio is delta VC upon delta IC at constant IB. It consists of three regions. First is active region, second is cutoff region, and Third is saturation region. Active region. In this region, base emitter junction is forward bias and base collector junction is reverse bias. The curves are approximately horizontal in this region. Then saturation region. In this region, on both the junctions are forward bias. Then in cutoff region, both the junctions are reverse bias. The region below IB is equal to 0 is called as the cutoff region. Then third is the transfer characteristics. In this, by keeping VC constant, change the base current and note the collector current. It is the ratio of collector current to base current at constant collector emitter voltage. Now, we will see the demonstration of this experiment. So here we can see this is the BJT common emitter input characteristics. Firstly, we have to put RH1 and RH2 at 1 ohm. Then set VCE at 1 volt. Or approximately to the 1 volt. Okay. In this firstly we set the VC is equal to 1 volt and then change the base to emitter voltage RH1 and note down the base current IB. We have to change RH1. Add to table. So this type we can see. Here is the graph of this input characteristics. Then after that, continuing the process, if you are taking VC is equal to 2 volt, 3 volt continuously, then we see as the collector to emitter voltage increases and base current will be decreases. This is input characteristic. Then we will see output characteristics. In this output characteristics, set RH1 and RH2 1 volt, then set the base current IB 15 microampere by adjusting this rheostat RH1. Okay. Then we have to take a vary collector to emitter voltage, which is RH2. This type of graph we will get. So this is the output characteristics. Precautions are the supply voltage should not exceed the rating of the transistor. Meters should be connected properly according to their polarity. And these are the references. So this is all about my experiment. Thank you.
I am Vaibhav Baliram Bharas. My call from third year, final year of BSc. College LPG Art and Science, Mahavidyalaya, Shirpur Jain, District Washim. My seminar topic is PN junction diode characteristic. Then introduction of my topic. My topic is to PN junction diode. Introduction. In PN junction diode, structure of PN junction diode. Semiconductor. Second point. Third point, p-type semiconductor and n-type semiconductor. Then working principle of p-n junction diode. Then aim of p-n junction. Then theory, diode characteristic, use as p-n junction diode. Learning outcome to study diode characteristic. Here is the structure of p-n junction diode. In this structure, we have to see p type of semiconductor and n type of semiconductor. In p type semiconductor, attach anode, and n type semiconductor attach cathode. It's a structure of p-n junction diode. Then next slide. P types. What is mean by p type semiconductor? In p type semiconductor, when impurity atom is add trivalent, when impurity atom trivalent add in pure semiconductor to form p type semiconductor. Example, aluminium. P type semiconductor form due to when trivalent impurity add in pure semiconductor form p type semiconductor. Then next, n type semiconductor. In n type semiconductor, when impurity atom is added in pure semiconductor, it's pentavalent. When pentavalent impurity add in pure semiconductor form n type semiconductor. Example of pentavalent semiconductor as antimony and arsenic. Working principle of p-n junction diode. The working principle of p-n junction diode can be broadly understood under two categories. Principle of p-n junction diode is divided in two types. That is, first one is forward bias p-n junction. Then second is reverse bias p-n junction. Principal work of p-n junction is important. p-n junction diode is important in daily life. It's used into design a circuit. In use of p-n junction diode using in forward bias p-n junction. Next, aim of p-n junction to draw IV characteristic curve of a p-n junction diode in forward and reverse bias. To study IV characteristic of p-n junction, it's important for to p-n junction diode characteristic. Theory of semiconductor. Its electrical conductivity lies between conductor and insulator known as semiconductor. A solid device containing have conductivity lies between semiconductor material, conducting material and insulating material is known as semiconductor. The common semiconductor material are silicon, germanium, gallium, arsenic. Silicon and germanium is the pure semiconductor which do not contain any impurities. Next, diode characteristic. This diode take advantage to p-n junction to convert AC to DC as a source of electricity and switch that lets current flow in either the forward or reverse direction based on the p-n junction diode. Means diode characteristic to flow current from AC to DC, alternating current to direct current as source of electricity. In forward bias diode, let current continue to flow while reverse bias diode block it. Forward bias diode let current continue to flow while reverse bias diode block it. Then p-n junction diode with forward bias. How to make p-n junction diode? How to make p-n junction diode? When a battery terminal of positive is always connected to semiconductor like p-type. When battery positive is connected to p-type, then this circuit is known as p-n junction with forward bias. In p-n junction forward bias, the graph is shown here. When if current is zero, if voltage current is zero, then voltage increases. If current is increases, then voltage is also increases. When apply zero voltage, gives zero current. When apply 0.3 volt, then apply 0.3 and break the germanium silicon. Experimental value of forward bias VI characteristic. In forward bias VI characteristic, when voltage is equal to 0, then current in milliampere means milliamperes 10 to the minus 3. When current is 0, then voltage is 0, then current is 0. When voltage is 0.2, then current is also 0. Then voltage 0.3 means current is 1, means conduct a current 0.5, then 1.2. When current 0.7, voltage is 0.7, then give 3 current in microampere. In any solid device, that in any solid semiconductor, germanium diode is conduct on 0.3 and silicon semiconductor is conduct on 0.7 in forward bias, only in forward bias. Then next, forward bias PN junction diode. Forward bias resistance of PN diode is very low. The forward characteristic of PN junction is not straight line. That is, it does not obey Ohm's law. So PN diode is non-linear device. In PN junction diode, germanium conduct on 0.3 volt and PN junction diode silicon conduct on 0.7 volt. It's conduct in forward bias of PN junction.
Hello everyone. A very good afternoon to all. The experiment, I am Komal Pusatkar from BSc third year, Shri Shivaji Science College, Amravati. The experiment that I will be demonstrating today is the experimental study of photoelectric effect. So let's begin with what is photoelectric effect. The phenomenon of emission of electrons from the metal surface when illuminated or irradiated by the light of suitable frequency or wavelength is called photoelectric effect. A German physicist, Heinrich Hertz, discovered the photoelectric effect in 1887. He observed that when radiation of suitable frequency is incident on the metal surface, electrons are emitted from the metal surface. So now let's see the experimental arrangement to study the photoelectric effect. So as we can see here, the simple experimental arrangement to study the photoelectric effect is as shown in the figure. It consists of an evacuated glass tube provided with a side tube for the incidence of light. The two metal plates are fixed in the tube, which has cathode and anode. The metal plate, which is also called as the photocathode, is of photosensitive material whose photoelectric effect is to be studied. A variable potential difference is applied between the two plates. The voltmeter measures the voltage between the plates and microammeter measures the photoelectric current. So now let's see what happens when the radiation is incident on the metal surface. When light of suitable frequency from source is incident on the metal plate, electrons are emitted. The magnitude of photoelectric current and kinetic energy of photoelectrons depend on many factors listed below. The first one is the potential difference between two plates. As we can see here, when radiation of a constant intensity and a given frequency is incident on the photosensitive surface, photoelectrons with kinetic energy ranging from 0 to a maximum value are emitted from the surface. If potential of anode B is made positive and increase gradually, Then it reaches to the saturation value. However, if the potential of anode B is made negative, then photocurrent decreases. If retarding potential is increased further, then photocurrent decreases and becomes zero at a certain value. The negative potential of anode at which the photocurrent becomes zero is called cutoff potential or stopping potential. At stopping potential, the potential energy of electrons is equal to maximum kinetic energy. That is, EVS equals to half of mv max square. Here Vs is the stopping potential. The second factor is the effect of frequency of incident radiation. So when radiation of varying frequency is incident on the metal surface, the stopping potential is found to be increased linearly with the frequency. The graph shows that the stopping potential is zero for frequency nu zero, which means that below frequency nu zero, emission of photoelectrons is not possible. The minimum frequency of radiation below which there is no emission of photoelectrons from a given metal surface is called as the threshold frequency. The third factor is the effect of intensity of incident radiation. If we keep the frequency of incident radiation and potential difference fixed at a certain value, the photoelectric current increases gradually with increase in intensity. Photoelectric current becomes zero at same instant when radiation is cut off. This shows that emission of photoelectrons is an instantaneous process. The last factor is the effect of photometal. It is observed that all lines have same slope with the different intercepts on frequency axis. Thus, it is concluded that threshold frequency is a function of photometal. Now we will see the characteristics of photoelectric effect. The number of electrons emitted per second is directly proportional to the intensity of incident radiation. There is minimum frequency called as threshold frequency for a given metal surface, below which photoelectrons are not emitted from the metal surface, that is, photoelectric effect is not possible. The third one is the maximum kinetic energy of photoelectrons is directly proportional to the frequency of incident radiation, and it is independent of the intensity of incident radiation. The last one is the photoelectric effect is an instantaneous process, that is, there is no time lag between the incidence of radiation and emission of photoelectrons. The classical physics could not provide us with the satisfactory explanation of the photoelectric effect. Thus, we have the Einstein's photoelectric equation. Classical theory failed to explain the photoelectric effect. The successful explanation of photoelectric effect was provided by Albert Einstein on the basis of Planck's quantum theory in 1901. Despite the popularity of Einstein's theory of relativity and his musings on black hole, Einstein's Nobel Prize in Physics was awarded for the discovery of photoelectric effect in 1921. Einstein assumed that when light incident on the metal surface, photon collide with the free electrons of metal. During the collision, photon completely transfer their energy to the electron. The part of this energy is used by the electron to just free from the metal surface, and remaining appears as the kinetic energy of electron. The minimum amount of energy required for an electron to just free from the metal surface is called photoelectric work function. Thus, according to the law of conservation of energy, h nu equals to half of 5 plus half of mv max square, that is E equals to h nu minus h nu 0, and this equation is known as the Einstein's photoelectric equation. So now let's see the characteristics of photoelectric effect on the basis of Einstein's photoelectric equation. When photoelectrons are emitted from the metal surface, the kinetic energy of photoelectrons is either positive or zero. Zero or positive energy is possible when incident frequency is greater than the threshold frequency. If incident frequency is less than the threshold frequency, then emission of photoelectrons is not possible. According to quantum theory, intensity of radiation is number of photons falling per unit area per second. Thus, when intense radiation is incident on the metal surface, there is greater number of collision between the electron and photon, liberating more number of photoelectrons. Therefore, photocurrent is directly proportional to the intensity of radiation. The third one is the photoelectric work function is constant for a given metal. The maximum kinetic energy of electrons is proportional to the frequency and independent of the intensity of incident radiation. As soon as radiation is incident on the metal surface, the collision between electron and photon occur, and at the same time, photoelectrons are emitted. Thus, it shows that photoelectric effect is an instantaneous process. Now, we will see the demonstration of all the theory that we have described here. So now, as we can see here, the arrangement that we have described, here is the microammeter, here is the voltmeter, here is the arrangement of anode and cathode, and here is the light source. So here we have chosen the material copper. The area of plate we set here to the 0.2 centimeter square, intensity of light to 10 watt per meter square, and the first aim of our experiment is to determine the threshold voltage, that is the stopping potential. So for that purpose, we will increase the reverse voltage and we will see the corresponding photoelectric current. So you can see here in the microammeter and in the voltmeter, as we increase the reverse voltage, the photoelectric current goes on decreasing. And at a certain value of threshold and at a certain value of voltage, the photoelectric current becomes zero. And that value of voltage we call as the threshold voltage. Secondly, we are determining here the Planck's constant. For that purpose, we will need the kinetic energy versus the frequency graph. And for performing the experiment, we have kept the value of wavelength at 100, 150 and 200 constant. And we have changed here the value of voltage to find out the corresponding threshold voltages. And after plotting the graph and finding the slope of the graph, we will get the corresponding Planck constant. So now let's see the findings of the experiment. As we can see here, as we increase the reverse voltage, photoelectric current goes on decreasing, and at a certain value of voltage, that is minus 7.8 volt, the photoelectric current becomes zero, and that value we calculate as the threshold voltage. The second one, determination of Planck constant. The slope of the graph gives us the Planck constant. Now, why do we need to study the photoelectric effect? What is the significance of it? The photoelectric effect is one of the most important founding stone of quantum physics. Study of photoelectric effect led to the important steps in understanding quantum nature of light and electrons and influenced the formation of concept of wave-particle duality. Thank you everyone for your patient listening.
Myself, Vaishnavi Vinodrav Khodke, BSc third year. So I represent the experiment to study the emission spectra of hydrogen, neon, and mercury vapors, apparatus, spectrometer, diffraction, grating, mercury bulb, hydrogen bulb, neon bulb, etc. So study the emission spectra to need the spectrometer as well the apparatus. Spectrometer is an instrument which is used to measure the intensity and other property of lights. Direction of all rays should be same, and for this light which is to be analyzed must be passed through the grating as a parallel beam. The main part of the spectrometers are to use to perform the your experiment and to observation, to use the main parts of spectrometer. So use a collimator. The collimator is used to produce the parallel ray. It consists an adjustment slit and convex lens. Prism table. The prism table is a circular in shape and in provided the three leveling screw, a central horizontal shelf for the mounting either a prism or a grating. Vernier table. The vernier table is a circular in shape and can be rotated about a vertical axis. Two vernier are attached to the vernier table and they move along the circular scale when the vernier table is rotated. The vernier table and hence vernier can be fixed in any position by means the radial screw. Fourth type is telescope, an object lens that focus on the entering parallel ray in a plane, so the real image can be observed. Crosshair located in the focal plane in the object lens. The telescope attached to a circular scale and can be rotated about the vertical axis to the center of the scale. We need to perform this experiment. The apparatus will be spectrometer, but actually cannot be perform this experiment in laboratory. So I this experiment perform in virtual lab, but need to theory to explain this experiment. When an atom or ion in substance got excited, then emit the radiation of a particular frequency. These radiation are seen in the form of spectra. There are several types of spectra, mainly first, continuous spectra. Continuous spectra is the band of the color is obtained. Absorption spectra is the dark line on a bright background. Third one is a emission spectra, bright line on dark background. In general, grating equation for the construction maxima is sin theta is equal to nm lambda. But m is order of spectrum, n is the number of lines per centimeter. Theta is the mean of the experiment performed. So the adjustment of the first we perform the experiment as a virtual lab. Yes, sir. We need to mercury switch on the light, placing the grating. To perform the experiment, angle of the telescope need to be 90 degree. So to perform the experiment, we need to the line of the green, blue, yellow, violet, red will be one light will be coincide with the 90 degree. So we move the telescope in right hand side. So red light will be coincide with the 90 degrees. So take the reading in vernier scale V1 and V2. Main scale reading will be 0, coincide with the 0. So the first reading is a 12.5, 23.5. One line will be 1 degree represented, and vernier scale will be used as a use the least count. So we take the first reading V1 and V2, and same procedure will be repeat in left hand side. So read the note down the reading V1 and V2. For the doing the real lab, setting the grating for the normal incident position. Vernier table is fixed in after the making the preliminary adjustment. Illuminate the slit with the mercury vapor lamp and make the slit narrow. The telescope in the line with the collimator coincide with the direct image in slit with the vertical crosswire. Standing the grating. Move the telescope to observe the direct image. Diffraction pattern are seen in the either the side of the direct image. Turn the telescope to the left, and vertical crosswire with the green line on the spectrum will be visible and coincide with the 90 degree. To calculate the final reading will be main scale plus vernier scale and into least count. So need to calculate the least count for the measurement. For the observation table, we observe this observation. The final result is the wavelength of prominent line mercury spectrum are given in nanometer in tabular column. Number of grating per meter 51.5. Thank you.
A very good afternoon to one and all present here. This is Sakshi Sunil Singh Pawar, student of BSc final year from Shri Shivaji Science College, Amravati. And today I'm going to demonstrate the experiment to study the Zener diode as a voltage regulator. Now, when we are talking about Zener diode as a voltage regulator, then the question arises that what do you mean by regulation and what is the need for the regulation? So, regulation is the process of keeping constant voltage across the load resistance regardless of variation of input voltage or load current. And the need for regulation is due to increase in input voltage and current across the load may be damaged due to overheating. To overcome this and to protect the load, the Zener diode is connected parallel to the load resistance in reverse mode. Zener diode. Zener diode is a special kind of diode which permits current to flow in forward direction as a normal, but it will also allow it to flow in reverse direction when voltage is above a certain value which is known as breakdown voltage or simply Zener voltage. This is a representation for Zener diode. Now the function of Zener diode, as I have earlier told that in case of in forward direction, Zener diode acts like a regular diode, but when we conduct it in reverse bias, when the voltage is above a certain value, this breakdown voltage is known as Zener voltage. Practically in reverse bias direction, no reverse current flow until a breakdown voltage is reached, and the breakdown voltage of Zener diode across the diode remains relatively constant. Zener diode as a voltage regulator. So voltage regulator is an electronic device, is an electronic circuit that provides a stable DC voltage independent of load current, temperature, and AC line voltage variations. A Zener diode of breakdown voltage VZ is reverse connected to input voltage source VI across load resistance RL and series resistance RS. Here we can see the circuit diagram for Zener diode. Here we can see the load resistance is connected parallel to the Zener diode and series resistance is connected in parallel. This is our variable voltage source and this is regulated output voltage. As long as the voltage across load resistance RL is less than Zener diode voltage VZ, the diode does not conduct, or we can say the circuit is open in case IS equals to IL. But when supply voltage Vin increases and the voltage across this load resistance is greater than or equal to Zener diode, then our Zener diode starts working. Now, when we apply KCL at this node 1, we get the source current IS equals to IZ plus IL. Now we can regulate this. We can regulate this Zener diode in two types, that is line regulation and load regulation. In line regulation, we keep constant series resistance and load resistance, and only input voltage is changing and output voltage remains the same as long as the input voltage is maintained above a minimum value that we call as Zener diode voltage. In case of load regulation, input voltage is fixed and the load resistance is varying, output voltage remains the same as long as the load resistance is maintained above a minimum value. So in case of line regulation, when we increase the input voltage, as long as we increase the input voltage, our input current also increases. With increase in input current, the voltage drop across the RS will also increase and thereby keeping the load voltage V0 constant. When Vn decreases, input current IS also decreases. With decrease in input current, the voltage drop across RS will also decrease and we get a constant regulated voltage V0. Also, for load regulation, when we vary the load resistance RL, when we increase load resistance RL, the load current IL decrease. This increase in current through Zener diode, that is IZ, and as a result of this, input current IS and voltage drop across RS remains constant, and once again we will get load voltage V0 against load constant. But when we decrease the load resistance, load current IL will increase. This decreases the current to the Zener diode, and as a result of this, input current IS and voltage drop across RS will remain constant, and we will get a constant regulated voltage V0. Now we'll perform the simulation. We will see the Zener diode is a line regulator. So here we can see this is our Zener diode. This is load resistance RL. Here is our source resistance. So in case of line regulation, we will fix our VZ Zener diode voltage at 5.1, and we will keep source resistance RS at 1400. Load resistance, we will keep it at 2500, and now we will vary our input voltage. We will start from 0. Here our Zener diode is not working. Now we will add this to our table and we will take the readings. We will increase it further. So now our input voltage is 3.8. Again, our Zener diode is not working. We will add this to table and we will take the reading. Now I will further increase this voltage. This is input voltage is 8.8, and here I increase, but we are getting constant regulated voltage, that is 4.1. Again I will increase it. This is 16.2, and our output voltage is constant, that is 4.1. We will take note of it. Again I will take a reading. This is 14, and our voltage is still constant, that is 4.1. I will add this to table. And now we will plot a graph. So here we can see after a certain value of voltage, that is Zener breakdown voltage, our output voltage has remained constant, and we have got parallel line for it. So from here we can say our Zener diode has worked as a voltage regulator. These are some of the applications for Zener diode. As we have seen, it is used as a voltage regulator, and these are all other applications of Zener diode. And thank you for watching.
This is Sonal Mandavkar from Shri Shivaji Science College, Amravati, BSc final year student. The name of experiment is determination of the Planck's constant by using the LED. First, we understand that what is the Planck's constant. Planck's constant is a physical constant was introduced by the German physicist Max Planck in 1900. Planck postulated that energy of light is proportional to the frequency, and the constant that relates them is known as the Planck's constant, that is E is equals to h nu. The Planck constant is a fundamental physical constant denoted by h, and it has a fundamental importance in quantum mechanics. It has exact value, that is h is equals to 6.626 into 10 raised to power minus 34 joules second, and its dimensions are m raised to 0, l raised to 2, and t raised to minus 1. The significance of Planck's constants are: Planck's constant describes the behavior of particles and waves on the atomic scale, and the idea behind its discovery that energy can be expressed in discrete units or quantities prove fundamental or the development of the quantum mechanics. In this experiment, we use LED to determine the Planck's constant because each color of LED has a different threshold voltage at which electrons start being produced. And by measuring these voltage together with a known values for emission wavelength, we can find a value for Planck's constant. Now we see that what is the LED? LED is a two-terminal semiconductor device. It consists of P-type and N-type semiconductors. P-type consists of a large number of, that is a more number of holes, and N-type consists of more number of electrons, as we see in the diagram. In unbiased condition, potential barrier is developed across barrier is developed across the PN junction of the LED. And when we connect the LED to an external voltage in forward bias, the height of potential barrier is reduced, and at a particular voltage, the height of potential barrier is very low, and LED starts to glow. That is known, the voltage at which LED starts to glow is known as the knee voltage. Once we reach the knee voltage, the current may increase, but the voltage does not change. The principle behind this is in this method, Planck's constant is derived by the voltage current characteristics curve for a series of different color LEDs. Now, the light energy emitted during the forward biasing is given as E is equals to H nu, that is SC by lambda. And if V is the forward voltage applied across the LED when it begins to emit light, that is the knee voltage, E is equals to EV. So we obtain the relation V is equals to SC by E into 1 by lambda. Now from equation 4, that is V is equals to SC by E into 1 by lambda, we can plot the graph and calculate the value of slope. The graph is plotted between the voltage across the vertical axis and the 1 by lambda on the horizontal axis. We get the value of the slope as S is equals to SC by E. To determine the Planck's constant H, we take the slope S from our graph and calculate H is equals to E by C into S. Using the known value of E by C, that is, we know that E is equals to 1.6 into 10 raised to power minus 19 electron volt, and the C is the 3 into 10 raised to power 8 meter per second. So we can calculate E by C is equals to 5.33 into 10 raised to power minus 28 CS per meter. And alternatively, we can write the equation as H is equals to E by C into lambda V. From this, we can calculate the value of the Planck's constant. Now we see the experiment. We make the connection as shown in the circuit diagram. Sorry, sir, this is a technical problem. As you see in the diagram, the circuit connections are the positive end of the LED is connected to the positive terminal of the voltmeter, and the negative terminal of the LED is connected to the negative terminal of the voltmeter. The positive end of the LED is connected to the end of the resistor, and the another end of the resistor is connected to the negative terminal of the ammeter. The positive terminal of the ammeter is connected to the rheostat, and So we have to change the rheostat so that the current is flowing through the LED. As the current changes, the voltage is also changes. We note when the LED basically glow, when the current flows, and we notice the value of the current on the ammeter. But if we increase the current, the LED further glow. But here we have to notice only the voltage at which LED starts to glow. That is the knee voltage. And here if we use the 4 LEDs, that is the red, green, blue and yellow. Red has a wavelength of 650 nanometer, and for this we take the slightly change the rheostat value, so the current is flows through the LED, and we note the voltage at which LED starts to glow, that is it becomes red. In this way we can notice or obtain the readings for the 4 types of the LEDs, that is red, green and yellow and blue. And by note down of reading of current and voltage from this experiment, we have to plot the graph between the voltage and the 1 by lambda. Here we see that the graph is as follows, is as shown in the diagram. The slope is calculated by the graph is plotted between the voltage and the 1 by lambda, and graph obtained is a straight line, and we just take any 2 points and take the slope of it, that is s is equals to y2 minus y1 upon x2 minus x1. That is, we calculate the value s is equals to 1.238 into 10 to the power minus 6, and we know the formula for the Planck's constant as h is equals to E into s by c. By putting the value, we get the value of h, that is equals to 6.598 into 10 to the power minus 34 joules second. The observation table is like that, and the result value of Planck's constant is 6.598 into 10 to the power minus 34 joules second. By using the graph, we calculated it, and the percentage error is exact value minus calculated value upon exact value into 100. So we take the difference and calculate the value, that is a percentage error of 2.8%. In this way, we can determine the Planck's constant by using the LED. Thank you.
My experiment is about black box. I am Khushali Anil Kade, student of BS third year from Shivaji Science College. The aim of this experiment is to identify and confirm the unknown device. The virtual representation of black box. As you can see, a voltmeter is connected across the unknown device, and resistor, ammeter and DC voltage are connected in series to it. For the identification of this unknown device, we will apply constant resistance. Then we'll note the voltage and current flowing through it, through the device by varying DC voltage. After plotting the graph between current and voltage across the device, we can identify it easily. Depending upon the VI characteristic of this unknown device, it can be either resistor, capacitor or diode. For diode, it can be any diode. It may be PN junction diode or Zener diode. It again depends on the VI characteristic of that unknown device. Here, this is the simplest form. This is the simplest form of the black box. We can also use one or more unknown device by connecting it in parallel or series by using different components. But we are dealing with the simplest form of this device. For that, we need to understand how voltage and current vary in each component I mentioned earlier. First, we will discuss VI characteristics of resistor. Ohm's law. The current through the conductor between the 2 points is directly proportional to the voltage across the 2 points, which means voltage is directly proportional to the current. Therefore, as you can see on the screen, This is the VI plot of resistor. If we get such a straight line graph, then we can finally confirm that given device is a resistor. If not, then we can move further to check other possibilities. Other possibilities are the unknown device may be capacitor. For that, in actual laboratory, we have to use CRO, but virtually there is direct changing frequency, so there is no need to bother about CRO correction. No. Capacitance is the ratio of the amount of charge stored in a conductor to a difference in electric potential, which means capacitance is inversely proportional to the change in voltage. You can see on screen that initially there is abrupt change in voltage, but as time passes, this change gradually with saturated voltage at one point. If these are the result of VI characteristics of the device, then we can conclude that capacitance is connected to the voltage. We will further check the possibility of diode characteristic and identify and confirm it. PN junction diode. PN junction diode is a diode in which half of the silicon crystal is doped with the trivalent impurity and half with the pentavalent impurity. The border of the N with PN is called junction. You can see the symbol of PN junction diode in forward bias mode on the screen. Forward bias diode. When positive of the external source is connected to the P side and negative terminal is connected to the N side, it is said to be forward bias diode. Width and potential barrier decreases. Potential barrier of silicon is 0.6 volt. You can see VI characteristics of PN junction diode in forward bias mode on screen. Here we can see that there is no current until the device crosses 0.6. After that, voltage rises exponentially with respect to current. So we may say that it is PN junction diode or silicon diode to be specific. Since 0.6 is the potential barrier of silicon, we can confirm it by checking the reverse bias characteristic of diode. Reverse bias diode, when positive terminal of external source is connected to the N side and negative terminal to the P type of diode, it is said to be reverse bias diode. Depletion layer width and potential barrier increases. You can see on the screen that there is gradual increase in current up to potential barrier. Once the voltage decreases further, we get saturated current. This is how we can confirm the given device is silicon diode. Zener diode. Zener diode is a PN junction diode. Its forward bias characteristic is same as that of the ordinary PN junction diode. In reverse bias, initially small reverse saturated current flows, but when the reverse bias reach particular value, the current increases suddenly. Zener diode is intentionally made to applied in breakdown region, and this breakdown voltage is also called as Zener voltage. You can also see the symbol of Zener diode on screen. Here is the VI characteristics of Zener diode. Initially, there is reverse saturation current on the once the breakdown voltage is crossed, there is voltage across the Zener diode remains almost constant. There is also reason why Zener diode is used as a regulator. If we find such graph in reverse bias mode, we can confidently confirm that given device is Zener diode. Now we will move to the virtual demonstration of black box experiment and use all this info to identify the unknown device. On screen, you can see this black box virtual representation. As I explained earlier, this unknown device is connected across the voltmeter, then resistor, ammeter, and DC voltmeter. is connected in series to it. First, we will put resistance and input voltage as a constant. Let make resistance at 1 kilo ohm and input at let give input voltage up to 5 volt. Now we will check the frequency and note the voltage. Sorry. We can take up to 15 to 16 reading for approximate calculation. I think this much is enough. Now we will plot the graph. Notice the change. Here you can see that the volt. Here you can see that initially voltage is gradually there is big difference between the voltage, but after some time there is voltage is saturated. Some there is a regulated voltage, you can say. So so from graph we can confirm that it is a capacitance. We will check it. As you can see, we include the correct result. So this is how you will find out which unknown devices applied across it. Thank you.
Hello dear friends and respected teachers. I am going to present and demonstrate on the Millikan's oil drop experiment. The oil drop experiment was performed by the Robert Millikan in 1909 to measure the elementary electric charges. The experiment took place at the University of the Chicago. Millikan received the Nobel Prize for Physics in 1923 for his study of the elementary electronic charges and photoelectric. The schematic apparatus for the oil drop experiment is as follows. This is then the DC supply capable for providing the potential difference up to the 10,000 volt. This is then the atomizer for providing for spraying oil into tiny droplets and telescope here. Inside this container, there are the two plates. The top plate is connected to the positive terminal. The top plate has a small hole. This hole allows a drop to enter this region between these two plates, and the top plate is connected to this positive terminal where the X-ray comes from here, which ionizes the gas present between these two plates. Latter, which in turn charges the oil drop present in the region, and initially the oil drop are allowed to fall between the plates in the absence of the electric field. The falling drop first accelerate because of the gravitational force Fg. Then due to the viscous force, a steady velocity reach due to the air inside, which acts in a direction opposite to the motion of the oil drop. Let's consider this velocity be v1. This velocity can be determined by recording the time required for oil drop to fall a certain distance with a constant velocity. For calculating the gravitational force, we can take consideration of the buoyant force, which is equals to 4 by 3 pi r cube rho minus rho air into g, where the 4 by 3 pi r cube is the volume of the oil drop, rho is the density of the drop, rho air is the density of the air, and g is the acceleration due to gravity. And using Stokes' law, F is equals to 6 pi eta r v1, where r is the radius of the drop and v eta is the viscosity of the air. When when the oil drop falls with a constant velocity, then there should be a no force acting on it. So these two forces are must be equal. That is gravitational force equals to viscous force. Therefore, r square is equals to 9 eta v1 upon 2g into rho minus rho air, from which r can be calculated if v1 is known and fg can be calculated using the viscous formula. Now, voltage is applied between these two plates. The top plate is connected to the positive terminal and force due to the electric field on the oil drop acts upward. That is F equals to QE, where the Q is the charge on the oil drop and E is the magnitude of the electric field. This force can do two things. First case, it may stop the motion of the oil drop. In that case, gravitational force is equal to electric force, that is Fg equals to F equals to QV. As we know that E is equals to V by D, where V is the voltage across these two plates and D is the distance between these two plates. Substituting this value, we get that Q equals to Fg into D by V. All quantities over here are known, so Q can be calculated. In case 2, the oil drop may rise up with a constant velocity. Let's assume this velocity be V2. This velocity can be calculated by recording time required to rise up to a certain distance. As the oil drop moves in upward direction, viscous force act downwards. That is 6 pi eta RV2. The oil drop rising up with a constant velocity, thus all forces acting on it should be balance each other. That is F equals to Fg plus Fp. Substituting value, we get Q equals to 6 pi eta RV1 plus V2 into D by V. Here all quantities are known, so Q can be calculated. Millikan performed this experiment and observed that the charge on oil drop is the integral multiple of the minimum charge was found to be 1.6 into 10 raised to power minus 19 coulomb. And from the J.J. Thomson experiment on cathode ray tube, charge mass ratio is a 1.6 into 10 raised to power minus 11 coulomb per kilogram. So he calculate the mass of an electron, which is found to be 9.1 into 10 raised to power minus 31 kilogram. From this experiment, he concluded that the charge over any oil droplet is always an integral value of P. Now we will see the demonstration. First, we choose the olive oil. Oil drop comes here due to the gravity in the absence of the electric field. We record the time to find the velocity with for a certain distance with a constant velocity. Now, voltage is applied. We adjust voltage. We observe that some drops will slow down but keep moving down. Few are stop moving and some drops are moving upward. We record this valence voltage and X-ray on. Here the voltage applied is 3500 volt and oil density is 920. Filling this observation table, we repeating this experiment, we find the charge on oil drop, which is found to be integral multiple of E, that is 1.6 into 10 raised to power minus 19 coulomb. Thank you.